So the COVID-19 coronavirus disease 19, 19 for 2019, it came out at the end of 2019, December, I believe. And it didn't really get to us until 2020, so it wasn't really relevant in our lives until 2020, but it did first come about in 2019. It's also known as the more complicated name SARS-CoV-2. SARS is a strain of the SARS virus. Back when I was in high school, you were probably way too young to remember about it, but there was a SARS outbreak in East Asia, gosh, a couple decades ago. So SARS stands for sudden acute respiratory syndrome. So it is a respiratory disease. COVID, coronavirus. I'm not sure what the 2 is, but there it is. So that's a breakdown of what all of these different things mean. So what is coronavirus and why has it taken over? So coronavirus or COVID is still a super new disease. We're learning new things every day, constantly doing research, finding out new things, literally every day. That's how brand new it is. It has spread all over the world. It is a pandemic. So here's some vocab for you if you're curious. There are things called epidemics and things called pandemics. Epidemics are a much smaller scale. So it's things like, a certain community or population within like a country, not very widespread. What we're in with coronavirus is a pandemic. So that is across many countries, affecting millions and millions of people, just many countries, different continents, spread all over the world internationally. So that's sort of the difference in that terminology there between epidemic and pandemic. So coronavirus is a pandemic. It's affecting almost every country, all the continents across the world. Maybe not Antarctica, don't actually know, haven't heard anything about them. Hopefully they're okay down there at that little research base on the bottom of the world. So coronavirus is spread through moisture droplets and it is considered airborne. So what that means is that it can travel through the air and not die when it leaves its host organism. There are viruses that are not considered airborne, things like HIV. Once that hits the air, it will quote unquote die. Again, they're not actually alive. It'll be non-viable. It will not be able to carry out its expected functions. So when we do things like breathe, talk, sing, yell, sneeze, cough, all of those things, we expel moisture from our body. We have these holes in our face that help us breathe, our nose, our mouth, and when we do things like just breathe, let alone talking and coughing and all that good stuff, we are releasing moisture from our body. Where does that moisture come from? Well, think back to cellular respiration. Cellular respiration tells us that water is a product of that reaction, and our body needs to get rid of that product somehow, and one of the main ways it does is through respiration. When we exhale, we're releasing moisture. So if you think about, it's a really cool day, like this morning maybe, you go outside and you see that like fog, and you're like, ooh, I'm a dragon. That fog is mostly water droplets. Kind of cool. But in those water droplets, if you are sick, you can spread the disease of coronavirus if you are infected. So because of this moisture expulsion, this is the reason why we need to wear masks. The masks help prevent that moisture from going out into the world. It keeps it tight and close to our faces so that if we come into contact with other people, it's not just like bleh, getting them sick, because we may be sick and not even know it. This is also why we social distance. You've been hearing 6 feet everywhere. We do live on Earth where there's gravity. So when things are in the air, gravity will pull it down to the Earth, the center of the Earth. When we talk, those moisture molecules will eventually drop down to the ground out of breathing range. So it's much, much less likely to affect someone or infect someone as it's dropping down to the ground out of the breathing area. So that 6 feet is about the distance it takes for things to sort of drop down and not be as dangerous. Here's a cool infographic that I really, really like. On the left here, we have our infected COVID-19 person. On the right, we have a healthy person. And it just shows you how masking and social distancing affect the risk levels of infection. So up at the top, the highest risk, kind of close together, nobody's wearing masks. That infected person is going to expel that moisture from their mouth. It's going to be airborne. That healthy person is probably going to get infected. There's a very high risk. Next, a slightly lower risk, that healthy person is wearing a mask. The masks are mostly to prevent the expulsion of that moisture from a person and less about protecting you from other people. But there is some sort of level of protection there. If you're wearing a mask, it does have a little bit of an effect. What is more effective is that if that sick person has the masks to prevent the spread of the airborne virus. The healthy person doesn't get as much of that exposure. The masks help contain most of that virus and moisture. But the best way is if both people are masked. So the person who's sick, containing their moisture, the person who's healthy, they also have slight bit of barrier to help protect them in case whatever might make it through the mask floats over to them. And the very, very, very best way is double mask. So both people are wearing masks and you have that social distancing. They are 6 feet apart. So whatever moisture does make it through that mask of the ill person, it won't make it over to the healthy person. So do both of those things. Always wear a mask, always keep your distance. So like we said earlier, COVID is still very new. We're learning brand new things every day. They're doing research constantly. But here are some things that we do know for sure. It is highly infectious. So that means it spreads pretty easily and pretty quickly. It causes respiratory tract infections. And those respiratory failures or infections or whatever is going on in there can lead to more severe illnesses, which can lead to death. So for example, at the very early stage of COVID, we were seeing an increase in cases of pneumonia. Pneumonia is a respiratory tract infection, and it was shown that the coronavirus was causing the pneumonia to take over some people. Pneumonia is really bad for old people, like super bad for old people. They're more vulnerable, generally speaking, to things like being sick. But pneumonia is bad news for old people. People who do not present symptoms, so asymptomatic people, we've heard this term thrown around a lot. So symptomatic, the A in front of that sort of negates it, so not symptomatic. You can still spread the virus. So if you're not feeling sick, you still might have the virus. We've found that COVID doesn't always manifest in symptoms in infected people. So I could have the virus and I feel totally fine. That means I can then become a vector. If I'm doing my yard work and my neighbor comes over to chat and neither of us are wearing masks, I feel fine, so I can be like, oh, well, I don't have the virus, I don't need to wear a mask. But if I'm asymptomatic, I still have that virus inside of me. And as I talk to my neighbor, and neither of us are wearing masks, we're pretty close together, I can give them that virus. I'm still harboring the coronavirus, the COVID. If I spread it to them, not great. They may be symptomatic. They can then possibly get that respiratory infection and die. Not good. So even if you're feeling fine, it's important that you mask up, keep your distance, because you still could carry that virus even if you don't feel any of those symptoms like the fever, the coughing, the headache, the body aches, all of the myriad of symptoms related to COVID. The other great thing you can do is wash your hands often. One of the best ways, because our hands touch everything. For eating, we have an itchy eye, all of that stuff. Whatever we touch could leave some virus behind if we don't wash our hands. So thinking back to our membranes unit and our viruses have that capsid that that sort of protects the genetic material of the virus. What soap does, if it's a lipid or protein membrane, the soap can actually break down that capsid membrane, and then it will compromise that genetic formation of our virus. So it will destroy the virus. So wash your hands. It takes about 20 seconds for that destruction to occur. So it's not just like water, soap, rinse. That's not enough. You have to wash your hands for at least 20 seconds. Longer is better just to make it extra sure. But if you need some sort of remembering device, mnemonic, I sing the happy birthday song 2 times. You can count. Lots of different ways to make sure you get that 20 seconds. Another thing that I didn't write on here, your phones. Your phones are disgusting. Wherever you go, your phone goes, right? Make sure you clean your phones. I try to make a habit of sanitizing my phone at least once a day. If I leave the house, I come home, wash my hands, sanitize my phone. Clean all your doorknobs. Even if you're not like going out to go like grocery shopping or something, if you touch that doorknob and you don't clean it, if you just go out in the front yard to hang out, you don't actually go anywhere and you touch that doorknob is still contaminated from when you went out to the grocery store. So make sure you wash your hands. You're not thinking about all the things that you possibly touch. Light switches too, especially your phones. Clean, 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 sanitize, sanitize. Try your best. I know it can be hard to remember. I'm gonna start getting excited soon. All right, so why is the COVID vaccine so exciting? So first, vaccines in general. They take about 10 to 15 years before they're ready. They're fully developed. They've done all of their research. They've done all of their clinical trials, and they've been approved for distribution by the FDA. 10 to 15 years. That's a long time. Now we're thinking about the coronavirus vaccine. This was developed in less than a year. That's incredibly fast. Like, oh my gosh. That's like a blink of an eye in terms of like the vaccine world here. Less than a year. However, it wasn't just some random scientist or pharmaceutical person who was just like, oh, what if we just did this vaccine? Boom. No, it was built upon decades and decades of research. The mRNA vaccine actually came from cancer research. So they were looking at how mRNA can be used in cancer treatments. And some brilliant person was like, what if we tried this for a vaccine? And look what happened. So our coronavirus vaccine is the very first FDA-approved mRNA vaccine for any disease ever. Ever. We're in groundbreaking medical science here. Someone got the vaccine, but they still have to wear a mask. We will get to that. Really, really good question. Okay, so we developed this vaccine super duper fast. We are breaking ground in science and medical technology. So what? Okay, getting too excited. Calm myself down. But listen, y'all, this is amazing. Right now, in science, in your biology class, we're learning about mRNA, we're learning about protein synthesis, we're learning about viruses. All of this stuff is happening right now in our world. It's not just some like, well, imagine if. It's like, no, this is actually happening right now. Amazing. Okay, I know you're all just as pumped and just excited as I am. Calm yourselves, take a breath. Okay. Now, let's look at the vaccine a little bit closer. How does it work? So what scientists have done is they looked at the code or the genetic information of our virus here, and they looked at all of the different proteins that makes up this little virus. And they go, oh, okay. What about this spike protein? This spike protein, so if we look at our virus here, we have all these little spiky things sticking out. These spike proteins are what attach the virus to its host cell. If we're thinking about our virus replication process, that is the very, very first step in viral replication. If it can't attach to the cell, it can't get inside and hijack all of those processes. So without the attachment, this virus isn't going to really be able to affect the organism very much. So they chose a very specific protein, this spike protein. It creates this more infectious virus because, again, without that attachment mechanism, the spike protein, it can't enter the cell to take over the protein synthesis process. So we're just going to call this the jerk protein. It makes this virus a jerk. Super infectious, no bueno. So they took a look at the DNA sequence, the genetic information, the code, and they made a transcription of this little protein. That's it. That's what's in our vaccine. Just a little piece of mRNA code. Kind of crazy. So no actual virus is entering our body. It's just the instructions. So we get our injection. It's just a bunch of random code, mRNA. We can't get infected by the virus just from mRNA. It's not a whole virus. It's just a piece. It's just, I don't know, mRNA. And so it enters our body. Our cells go, hey, look, some mRNA. Let's make some copies and proteins. So it'll go through the transcription process. It'll go through the translation process. We'll make some protein of this jerk protein. Again, it's not the actual virus. It's just a part of the virus. It's just that little protein. Proteins can't hurt us. It's just like, you eat a steak that's made of protein. Can't hurt us. It's not the actual virus. So we have now this little jerk protein floating around in our body. Our immune system goes, wait a minute, hang on. This doesn't look like something that's us. I don't like it. What the heck? It'll start attacking that jerk protein. This is when our immune response comes in. This is the side effects of our vaccine. Not nearly as severe as getting the actual virus, but it's, some people do experience side effects, chills, little tiny fever, maybe some aches here and there. And if anything, it lasts a couple of days. Some people don't experience the side effects at all. Much, much better than the actual virus, which can take you out for a couple of weeks. All right, so now our immune system, we defeated it. We know exactly how to kill it, destroy it. Again, it's still just the protein, not the whole virus. But it remembers. We have those memory cells. All right, if we ever see this protein again, we know it's bad, and we know we can kill it. We don't have to do this trial and error. How do we do it? We know exactly. We can zero in. Boom, this is how we kill it. So then, our immune system is remembering these proteins. And we go out in the world, we get exposed to the real coronavirus. Even though our body has never actually seen the virus before, it remembers, hey, I've seen this protein before. Are you joking? This guy, we're going to get it. We don't like him. We're just going to destroy it. And our immune system will efficiently launch an attack, killing these little viruses, making sure they don't come back, because we've had that practice. We recognize that protein on the outside. Therefore, the outside of that virus will be compromised. It will no longer be able to take over our bodies. Amazing. So we don't actually need to infect ourselves with the real virus. All we need is just a little bit of code. Okay, so what if the virus, no worries, glad you made it back. What if the virus mutates and it no longer makes this jerk protein? Well, since this specific protein that the scientists chose is what attaches it to the cell, it'll be less infectious. If it can't get into your cells to then take over and make more of itself, it's kind of at a disadvantage. So that wouldn't be a great mutation to have. This is what makes the vaccine so cool. Scientists chose a very specific protein with a very specific function that if there is some sort of mutation, the virus will be less viable. It won't be as infectious. It won't be able to take over at the same sort of magnitude as it would if you didn't have that vaccine or it didn't produce that jerk protein. So when I made this slideshow, it was about a month ago, January 18th, not a month ago, 10 days ago. Things obviously have changed. This is a novel virus. We're learning new things. Things are changing constantly all the time. So there have been a few updates. To answer your question, if someone got the vaccine, would they still have to wear a mask? Yes. So as of right now, Research is showing that even if you yourself are immune to the virus, you can still spread it. So if I catch the vaccine, even though my body is fighting it, I still have the virus inside of me. I can become a vector. So until my body defeats the little bit of virus that it encountered, I can spread it. Good question. All right, so as of 2 days ago, I updated a little bit here. There are a few variants. The most relevant one right now is the UK variant, the one found in the United Kingdom. All of these variants have weird number letter identifications, but it is called the B117. A lot of times in the layman articles, they just call it the UK variant, but scientists and researchers like to have a more numerical and quantitative sort of naming system here, so I guess they use letters and numbers. Anyway, what they're finding in the UK variant is that it spreads more easily and quickly than other variants or mutated versions. They're seeing that instead of the virus harboring in our lungs, like super deep down in our respiratory tract, it's starting to sort of stay in the back of our throats and our sinuses, so that when we sneeze and cough and talk, a lot more of it is getting out of our bodies because we're talking and coughing and sneezing and all that sort of stuff. So that's what makes it a little bit more infectious, a little more easily and quickly that it spreads. So far, there has been no evidence that it causes any more severity in symptoms or increase in risk of death. So it's about on par with the original. So still not great, but not any worse. We have seen some cases spread to the US and Canada, but again, not any worse than the original one, but it is starting to mutate. Next up, we're going to talk about the South Africa variant, also known as 1.351. Studies have shown that it shares some of its mutations with the UK variant. So they may be, it may have come from the UK variant, we don't know. Due to that, they have a lot of similarities. It has not yet shown up in the US. The Brazil variant. This one is a little bit more spooky. It's also known as P1. It contains mutations that may affect its ability to be recognized by antibodies or our immune memory cells. So if we get the vaccine and we come in contact with the Brazil variant, there's a possibility that it may not be recognized by our immune system. There are some changes that make it possibly unrecognizable to our immune cells that have had that practice with the vaccine. It says it has not yet been detected in the US. However, I got an update on my phone about an hour ago saying that the South African variant has now been detected. So I'll have to change that, update that as of an hour ago. So the Brazil one is still not yet in the US. That's the little bit scarier one in terms of the vaccine. But the South Africa one has actually now been found in the US. So why do we care about all these variants? What's the big deal? As the virus spreads, each new host is making more and more of these viruses. And every time we replicate, there's going to be this opportunity for a mistake to happen. So we're making copies of all of this code. Things happen. It can misread something. It can insert something on accident. Stuff happens. So the more people who are infected, the more copies of RNA are getting produced, the more chance of a mistake happening or a mutation. And if that mutation changes enough, so if it's something like a big frame shift or a nonsense or a missense mutation, that will change things. And if it changes too much, our immune memory cells won't be able to recognize those proteins from the vaccine, or if you've had the virus. This is why we want to vaccinate as many people as quickly as possible. Because if we vaccinate people, there won't be as much chance for those mutations to happen because they won't be getting sick. They won't be infected with the real actual virus. We reduce the number of people getting sick. We reduce the opportunities for mutations. So what does our future look like? Hopefully, if we can get the vaccines rolled out a little quicker, we can get enough people vaccinated. We won't have to deal with all of these crazy, scary new mutations. Best case scenario, we'll just need a booster shot every year. So just like the flu shot, we need a new flu shot every year. They'll be like, here's some new mRNA of some variants we found, so you're protected for the next year. Not nearly as bad or scary. Probably just add it into your flu shot, honestly. All right. Any more questions? Are the teachers getting the vaccine yet? Not yet, unfortunately. Things are getting jumbly. Actually, I have our vaccine schedule for California. So phase 1A, we've done a lot of this. So each state is different on how they're determining the rollout of vaccines. So for California, we have phase 1A. It's about 3 million people. We're focusing on healthcare workers, so people working in hospitals, frontline workers in contact with coronavirus patients, and long-term care residents, things like nursing homes. Lots of high population, not very much space. Want to get those people who are the most at risk. Those long-term care residents are oftentimes geriatric care, older people. They can be more at risk, so we want to get them vaccinated. We started phase 1B, so we're in the middle here of this 1B tier 1. We're focusing on individuals 65 and older. Again, older people. We want to protect our grandmas, our grandpas, our, in my case, my parents. You know, they're more at risk. If they get sick, there's a higher chance that they will have more severe symptoms or even get or even die. Also in that tier 1 of 1B, those at risk of exposure at work in the following places: education, hey, that's where we are, and childcare. Still working on getting teachers vaccines. Emergency services, paramedics, firefighters, police people, food and agriculture, our sort of farmers. Make sure that these important people get the vaccine. Tier 2, those at risk of exposure at work in these places: transportation, logistics, industrial, commercial, residential, and sheltering facilities, critical manufacturing, places like meat packing plants, congregate settings with outbreak risk, incarcerated peoples, so prisons, again, high population, tight living space, more risk of exposure and infection, high infection rates there, and the homeless population. Phase 1C, individuals, again, in the more middle age range, 50 to 64 years of age. After them, we're going to go down in age to 16 to 49 with underlying health conditions. If you have asthma, if you have heart problems, things like that, that can increase your risk of, you know, the severity of your COVID-19 symptoms. Those working in water and wastewater, defense, energy, chemical and hazardous materials, communications, IT, financial services, government operations, and community-based essential functions. So again, people who are working around a lot of other people. After phase 1C, we move on to the regular general population with no underlying conditions, healthy people in the 16 to 49 age range. I've gotten questions in the past about, well, why aren't kids getting the vaccine? Well, again, the vaccine is very, very new. There is a sort of ethical problem with testing, trials, medical stuff with children that hasn't had enough time to experience, you know, the full range of side effects. I believe the Moderna vaccine has an age limit of 16. That's the youngest you can be, and I think the Pfizer is 18. Hopefully, once we get a little more of the vaccinations under our belt, we're getting more data about how it's affecting people, if there are side effects, what are the side effects, how severe are they, things like that. Hopefully we can reduce that age range and get kids vaccinated as well. All right. Any other questions, comments, concerns?